Okay. We will start. So welcome everyone to the Tract-Anat Club for the month of April. For this edition, we decided to be a bit different and go with a panel approach where we have three people that Ariel is going to introduce a bit later. He's going to be our host because for this one, I decided to include myself as a part of the panelists. So we are going to present a small 10-minute presentation each. And then at the end, we're going to discuss together about what we just presented. People will pitch in with questions if you have any. So we will start, and Ariel is now the host and in charge. So Ariel, it's to you.
Thanks a lot, Francois. Hello, everyone. My name is Ariel Rheault. I'm a research faculty member at the Department of Psychology at the University of Washington in Seattle, United States. And it's a pleasure to introduce today's panelists. The panel today will present all kinds of recent technical advancements that reduce the computational demands or optimize resources for tractography-related analysis. We'll explore in this panel how innovations like GPU acceleration, mathematical techniques, code optimization, pipelines, and workflows can reduce the demands of tractography, accelerate it, increase the scale and scope of tractography. And we'll hear three short presentations followed by a little bit of panel discussion where the audience can also participate. So I will introduce each one of the speakers before they give their sort of short 10-minute presentation. The first presenter is John Kruper. John is a PhD student here at the University of Washington, and he works at the intersection of psychology and data science. He's particularly interested in how white matter in the brain relates to different conditions, and he uses tractometry in order to study those kinds of questions. John, take it away.
Hello, everyone. Today I'm going to be talking about GPU accelerated tractography. So first off, I wanted to spend a few minutes talking about what is a GPU. You've probably heard that acronym thrown around, either in the news or for your work, but it's not often explained why it is. GPU stands for Graphics Processing Unit, and that's because they were initially designed to accelerate graphics rendering. However, they've been made more flexible alongside the need for more complicated graphics programming, and now they're very generally useful for parallel computations in linear algebra. So on the left here, I show a figure, which is sort of a rough schematic of the difference between the GPU, which is the graphics processing unit, and the CPU, which is what you're probably normally using to run your code. So with the CPU, you might expect to have on the order of four different cores, where each of these cores, if you're not familiar with hardware, no worries. The idea is these are each little workers that are running through and executing your code. And each of these cores might have their own on-chip memory. But the basic idea is you have on the order of 4 of these little workers, so you can do some multiprocessing on the CPU, but not too much. On the GPU, you don't necessarily have more memory, but you have significantly more cores, and that's what's shown on the bottom left. So you have many different workers doing things in parallel. All right, let me talk a little bit about the history of this to get a better idea of where this comes from. So initially, graphics processing units were used for preset functions. Basically, if you could imagine trying to render something like for a video game, trying to render a complicated scene, you want little workers running small, maybe preset programs for each pixel on the display. However, in 2001, there was a need for more complicated shading in video games. And so people wanted to be able to do some limited programming on the graphics on the GPU in order to get better performance out of them. And then through to 2003, a group actually went and reframed linear algebra problems into graphics primitives, which is really interesting. And what that allowed them to do is use this GPU to then solve linear algebra problems faster than on the CPU. And then after that, in 2006 through 2008, there was a series of developments to try and make GPUs just more generally useful. And now, whenever you want to do any task in parallel, the GPU can be used for general purpose computing. All right, so I'll talk a little bit about what sort of problems are useful on the GPU. So like I've been mentioning, parallel computations, especially computations that can access memory in predictable ways, and it can be done extremely fast. I pulled off some rough numbers from some hardware from 2022. The NVIDIA A40 has around 10,000 cores, where the Intel Core i9 has around 16 cores. So there's many orders of magnitude more workers on the NVIDIA A40, so you can do many more things in parallel on GPUs. And many known linear algebra problems have known GPU-based approaches, which are faster than CPU-based approaches. But people don't use the GPUs for everything, and there's some reasons why. Some disadvantages is that the GPUs have limited on-board memory, and then it can be slow to transfer memory back and forth between the GPU and the rest of the computer. And also, each individual core on the GPU is going to be much slower than on the CPU. They're less optimized for each individual worker. So any computation where it can't be done in parallel, where each step in your program necessarily depends on the previous step, will be slower on the GPU. All right, so maybe you've been thinking so far about different ways this could be applied to what we do with neuroimaging. I've thought of a few ways. The first one is streamlines, which is what the rest of this talk will be focused on, which is that each of these streamlines can be generated in parallel. For most tractography algorithms, the generation of one streamline does not depend on another. So you can imagine generating multiple streamlines at the same time on the GPU. You can also imagine fitting models to different voxels in parallel on the GPU, or for solving linear algebra problems, which can be useful, for example, for image registration. So maybe I've gotten you a little excited about using the GPU for solving neuroimaging problems. There's a few tools you can use for using the GPUs. First, if you have NumPy code in your own existing databases or SciPy code, you can replace it with a library called QPy. QPy tries to re-implement a series of NumPy and SciPy methods, not all of them, but a lot of them, in using the GPU. So all you would have to do is replace your import from NumPy or SciPy into QPy, and then it will perform these array operations on the right I show, for example, doing a sum, and it will perform these on the GPU. And this sort of naive substitution, depending on your problem, could net you a big speed up if you have access to a GPU. The second way to do it is to write code specifically for the GPU. There's a variety of different languages to do this, but this can be complicated if you don't want to spend a whole bunch of time doing this, or learning a new language, or learning about the hardware, or whatever. And so the third way is to use existing code that other teams have already written to take advantage of the GPU for neuroimaging problems. And that is GPU streamlines. So this summer, I worked on a GPU implementation of probabilistic tractography. This was developed in collaboration with NVIDIA. Using this, you can generate streamlines from 1 million seeds, which is about 2 million streamlines, in under 1 minute using the NVIDIA A40. This is in contrast to, this was based off the DiPy library, diffusion imaging in Python, which took over 10 minutes to do the same task. And that's with the recent updates to DiPy. So this is it's about a 20-fold speed up. This GPU streamlines, we tried to make it as convenient to install as possible. If you already have access to an NVIDIA GPU and you have CUDA toolkit, or on your server you have access to a GPU, you can install GPU streamlines using pip or Docker. or if you were familiar with PyFQ and want to do bundle recognition, you can install it alongside that. It does require the Kugel toolkit and CMake, which you probably need for running almost anything on the GPU. And it does interoperate with DIPy, diffusion imaging in Python, which is a very popular library for running diffusion imaging algorithms in Python. It's based on that whole interface and works in that ecosystem. And here's a link. All right, so in order to get an idea of how fast GPU Streamlines is and what you can do with it, I wanted to compare it to some of the existing implementations for tractography in the field. So first off, DIPy has implemented multi-threaded tracking using Cython, which allows developers to write Python code with optional C syntax extensions. This allows the Python code to be something that looks like Python to be compiled into C, which is very fast. You can read more about it at the DIPy website. Another very popular library, which you'll hear about more later in this panel session, is MRTrix3. This is also an open source software package for analyzing diffusion MRI data. It contains algorithms that are implemented from scratch in C++, so it's generally very fast. And in this case, I benchmarked against their default tractography, which includes iFOD2, which is slightly more complicated than generic probabilistic tractography. It involves sampling candidate paths over multiple FODs. So it's a way of integrating information across multiple voxels before doing tractography. And finally, I compared it to an experimental implementation of tractography, which can be run on the GPU from Scilpy using OpenCL. OpenCL is an interesting language. It's a low-level API for heterogeneous computing. It can work on coordinated CPUs on a server, GPUs, a whole bunch of different hardware, and enables coding for parallel computing that's much more general than just NVIDIA GPUs, which is what GPU Streamlines is written for. All right, so on the x-axis of this plot, you see the number of seeds used to generate the tractography. On the y-axis is time, and we're looking at 4 different implementations. Purple, these first 2 orange ones are DIPy using either 1 threads or 4 threads from your CPU. You can see it takes 10 minutes to generate tractography from 1 million seeds, 3.6 minutes if you use 4 threads, and only 38 seconds on the GPU. Similarly, if you're using the CPU, it would take 105 minutes to generate 10 million seeds, 37 minutes with 4 threads, and then only 5 minutes on the GPU to generate seeds from 10 million seeds. So that's very fast and allows you to generate huge amounts of streamlines in almost no time at all. We're going to look at this again now on a log scale to get a better idea of the consistent speedup you get from using the GPU. Here we've added the MRTrix implementations, which again, I tried to make it as similar as possible to the DIPy setup, but they're also doing iFOD2, and there's some other differences. So this is not a direct comparison. It's just to get orders of magnitude. Oops. Go back. Oh, sorry. Let me go back. Yeah, so you can get in DIPy a 3 times speed up from using 4 threads, but compared to using a single-threaded CPU, you can get about 20 times speed up from using the GPU and generate tractographies from 100 million seeds in about an hour, which is extremely fast. All right, so in conclusion, some parallelizable algorithms can be made much faster on the GPU. This can be useful in large neuroimaging data sets, which are becoming more and more available. This can be large in terms of the size of the data or the number of images in the data set. Algorithms that were once limited by computational constraints can become faster on the GPU, which is why we're currently working on parallel transport tractography, if you've heard of that, and trying to speed up fitting MSMT. Additional work on GPU accelerations, if you're interested, you can check out this repository, DIPy/QDIPy. And you should think of your think of your own use cases where you can use GPUs in your own work. All right, thanks to everyone who helped me on this, and thanks for listening.
Thanks, John, for that presentation. And instead of taking questions right now, please reserve your questions later for the panel discussion and move on to the next talk. The next talk will be by Francois. Francois Rheault is an assistant professor of computer science at University of Sherbrooke. His research centers on improving tractography algorithms and creating efficient processing tools and pipelines. He contributes to open source Python libraries like Scilpy and Dipy. Take it away, Francois.
Okay, so I assume you can see my slide right now. Perfect. Thank you very much for the introduction. The title of this short presentation is Limitations Foster Innovations. You will understand why I call it like that just a bit later. To give you a bit of context on my presentation, I'm going to refer to a few scripts and operation and function that are open source. They are available in the library called Scilpy, where we have around 190 scripts right now. They are often based on Dipy, but they are kind of it's a library that provides scripts that are self-contained operation with CLI, command line interface. Also, if you know MRTrix, Scilpy is kind of a Python alternative, but we do put some emphasis on post-processing of tractogram, bundles, and streamlines. So we have a variety of scripts that are often analogous to MRTrix or Dipy, but we do have some manipulation scripts that are utilities to do some prototyping very fast, like flipping streamline, cutting streamline, coloring streamline. So our goal is to play with streamline very often. So this is the context. This is a library I will refer to a lot during the presentation. And the reason why my talk was mentioning limitation that foster innovation is that our library is in Python. It's not as optimized as C++ or Rust. So a lot of our scripts are considered slow or heavy in memory because we are not finely controlling the memory usage and the operation. But sometimes these limitations, because of Python, emerge some innovation because we are forced to overhaul the whole script or modify the fundamental of the operation. So today I want to present a series of incremental development that converge into a usable tool or pipeline for bundle segmentations. So over the years, we kept updating our scripts and our methods to work well together into something usable in real use case, for example, for the clinic or at the scale of limited processing time. So the innovations I want to talk about today are streamline compression, a new tractography file format called TRX, and bundle segmentation that over the year they combine into bundle seg, that all of this works well together. So the first one is very simple. Most of you are aware that tractograms are difficult data structure to play with. They use a lot of memory because we have to explicitly store millions of streamline. Depending on the step size, we have hundreds of points for each streamline. This can get to tens of gigabytes very fast. Well, something as simple as streamline compression, where we remove collinear points. So here you have a tiny drawing that's fairly simple. If we have a small step size, we generate a lot of points that can be contiguous visually. They are locally smooth. So we don't need to keep all points, because locally, if we just simplify this to just keep the first and the last point of a few millimeters at the time, we will end up having a low error and removing a majority of points. So this ends up removing some small difference in terms of voxel and some millimeter modification, but overall it doesn't change the shape of the streamline, and we can quickly remove 80% of the points in probabilistic tractography, or almost 90% of the points in deterministic tractography. In the context of this presentation, this simple contribution, well, it removes the majority of points, so you have much lower RAM requirements, so memory requirement, or faster read and write operation for all subsequent operation. By simply doing this, you lose almost nothing, and you end up speeding up everything that comes after and simplifying your memory management. The next thing I want to talk about is the TRX file format. So in the context of this presentation, I'm going to stay fairly simple. The idea was that a few years ago, we had the idea to standardize file formats to have a clear specification that would take the best of TCK and TRK It's still work in progress, but the idea was to allow us to finally control the data type and to allow us to load any streamline or chunks of streamline efficiently using memory mapping. So basically, your data stay on disk, but it's contiguous on disk and allow you to save and load very efficiently and control your data type. So floating point precision, for example. The idea here in the context of this presentation is that you load only the streamline you need when you need them, and you control the representation of the bit size for each point, which allow you to have much faster read and write operation, but also lower RAM memory requirement. And this is a file format that would be compatible with compression. So it combines very well with what I just mentioned. You can compress your tractogram and have a factor almost 10 smaller tractogram. So instead of having 10 gigabyte, you have 1 gigabyte tractogram. And with this, you can even compress it further by controlling the data type. And you will end up with a tractogram that's almost 20 times smaller than originally at almost no cost in terms of shapes of streamline and coverage. This file format can be used in Scilpy for some tool. But the last one I want to talk about that's the most important is the bundle segmentation. So this is the biggest innovation in the three. For those of you that are not familiar with bundle segmentation, typically when we do a whole brain tractogram, we can do, for example, connectomics, where we check connection from cortical region to cortical region. But another approach is to do bundle segmentation for bundle of interest, where we manually place region of interest, or we use an atlas to say, show me all of the streamline that start in the brainstem, go in the precentral gyrus, go into the internal capsule, and you end up with a bundle of interest that has a name, typically like the cortical spinal tract or the pyramidal tract. So that's using region of interest. This is great, but sometimes with pathology or with thousands of data set, it's a bit difficult. So in Scilpy and Sherbrooke, we typically use a shape-based approach. Initially, a few, let's say, years ago, we were using RicoBundle that is available in Dipy. It's a atlas-based segmentation based on the shape of streamline. So if we take the naive approach, we have millions of streamline in our tractogram. We have an atlas that represents what the bundle should look like. And if we do it naively, we do a comparison of every streamline to every streamline. And we find the matching neighbor. The idea is to say, if I find a streamline that is similar to my atlas, it must be the same bundle. If we do it naively, this would be trillions of comparison because we would compare every streamline to every streamline. The reality of RicoBundle is that it uses clusters. So we do a clustering operation to reduce the computation by simplifying the spatial component of the streamline. So instead of having thousands of streamline in the atlas and millions of streamline in your tractogram, we end up with a few thousand streamline in each, and then we have a few million of comparison of cluster to cluster. And the idea is that with the streamline-based distance, we can associate them and say, this atlas look like these streamline, and we have a segmentation. However, a limitation in RicoBundle is that there is a clustering step that's really, while it really improved the computation, it's really hard to fine-tune this clustering parameter. The clustering is far from perfect. There is some stochasticity to it that makes it hard to generalize. It has a specificity and reproducibility challenge sometimes. This is an example of RicoBundle being run on two sets of identical streamlines. So I ran the algorithm twice on the exact same streamline, except I shuffled them. And the idea is that if the algorithm was perfect, you would see only one color here because you would get the same segmentation twice. Here we see some orange and some pink, meaning that the segmentation did two different results and they did not overlap perfectly. There is some problem there. One way to solve this is to change the clustering threshold to put a number that's much smaller. The idea is that if you have smaller cluster, there is fewer error, but you end up slowing down the algorithm way too much. If we push that parameter down, you can end up with a day of computation if you put it really low. And this triggers some innovation because if we were in C++ or in Rust, we could tolerate that slowdown because we were very fast in the first place. The idea here is that we were limited by Python, so we could not push that parameter down. So we solved this. I say we, but it's really Etienne Saint-Onge that solved this. He removed entirely the clustering by computing I'm going to read here, by computing a streamline to streamline distance using hierarchical search based on a tree structure. So for those of you that are familiar with a KD tree or a NOC tree, it's a search of streamline in kind of a decision approach with a search instead of being an exhaustive comparison. So this is kind of going like an algorithm that's n square comparison to an n log n comparison, for those of you that are familiar with algorithmic complexity. To keep it simple, this in the context of tractogram is a factor 1,000 times faster than an exhaustive comparison. So this is really impressive in terms of speed up, but it also increases reproducibility and specificity, and it makes it easier to use. So it's really a win on all sides by removing clustering and digging into data structure and algorithmic approach. And those three things combined together end up with a nice pipeline that we have in Sherbrooke that over years we improve each of these independently, and they converge into a usable method that can now segment the tractogram with 3 to 4 million streamline into 50 to 70 bundle, depending on the white matter atlas, in less than 10 minutes with a few CPUs and a reasonable amount of RAM. So the idea is that before, this operation could take 1 hour, for example. If we push the parameter as low as possible for clustering, could take a few hours. And now it's not only better, but it's faster, and the amount of RAM is really reasonable. So all of these incremental technical innovation, they really merge, they converge into a usable tool. And for example, what John was presenting earlier, if tracking takes 1 minute and now this takes 5 to 10 minutes, we can go from raw diffusion to tractogram to bundle in a much shorter span. And this was my my conclusion, is basically by combining small innovation together, and in our case, it's because of Python. Sometimes we combine them because we had to, we can really speed up some process by making them work well together. Here I have a few citations. I'm going to put a link to my presentation in the chat if you're interested. The TRX file format repo is here, and I have a few example atlas here if you want. So that's all for me. Thank you very much.
Thanks, Francois. And again, we can please reserve your questions to the end of the panel. We'll continue on to the next speaker. The next speaker is Robert Smith. Robert is a senior researcher at the Florey Institute in Melbourne, Australia, dedicated to making tractography more quantitative for connectomics and fixel-based analysis in his work. He is one of the lead developers of MRTrix3 and participates in multiple open source initiatives. Please, Robert, go ahead. You're muted still?
Yep, sorry, I lost my controls for a moment there. So I'm going to try to simultaneously give some insight after 15 years in the intersection between research and software engineering, and then try to exemplify that with a few case examples of recent collaborations. So the way I think about how computational optimization can contribute to research software is it exists on this spectrum of how applicable any particular proposals are. So at one end of this spectrum is improvements to, for instance, tractography algorithms that are going to be applicable to any tractography related analysis that's using that piece of software. In the middle, you may have research projects where you want to improve some specific aspect of the software that will benefit that particular project, but will also benefit other projects once it becomes available to the wider community. And at the opposite end of the spectrum is this idea that an individual research project may warrant dedicated software engineering investment to either facilitate or expedite that one project. So I'm going to try to give some examples of each of these three. So at the close end is, so I've been working with the MRTrix3 software for about 15 years. It's well known for being written in C++, which is less accessible to researchers and does require a fair amount of training to get a grasp on, but it is very efficient being a compiled language. We we've put a lot of effort into expediting implementing various algorithms to make use of multiple threads, and we have this generic backend within the API. I often tell people that I can turn a program from single-threaded to multi-threaded in about 30 minutes of coding. And this comes about by this framework whereby we can define any type of data that we want to be either input or output to a multi-threaded process, and the backend deals with all of the communication with the threads. And so this can be used for streamline generation itself, but also for any kind of other post-processing operations. We've also been putting a little bit of energy lately into the build system of Matrix 3, and we're wanting to put a greater emphasis on this idea of external projects that make use of our API to facilitate their software developments, but don't actually have to be a part of Matrix 3 itself. They can just make use of the tools that we have available. And I will also note that the implementation of new tractography algorithms is it makes use of C++, what's called templates, which makes it exceptionally fast. But it's also a very simple interface in that to create a new tractography algorithm, you literally just have to define two functions. One is from a given start point, can you initialize a streamline? And then the other is from the current streamline position, give me the position of the next point. If you can define those two functions, you can implement a new tractography algorithm in Matrix 3, and you can inherit all of the other benefits of operating within that ecosystem. In the middle of the spectrum is this idea of software developments that are targeting particular project initially, but have broader applicability. So I was on this collaboration a couple of years ago where we did, it was actually closer to 45,000 scanning sessions from the UK Biobank. And so we had to put a lot of forethought into this because we're dealing with not only a large number of scanning sessions, but also we wanted the data that we produced from it to be very broadly applicable. We didn't want to just do our own personal preference of connectome reconstruction and then expect everybody else to be happy with that. So there was a lot of balancing to be done between wanting to support a lot of different possible connectomes versus being limited in the size that UK Biobank would be willing to store and share data. But we also didn't want the data to be too cumbersome to interact with. So here's the general approach that we came up with here. One was that before we actually hit the go button on doing 45,000 reconstructions, we wanted to identify potential software features that would be beneficial to that and implement those ahead of time and make use of them. We wanted to save space, we would only pre-generate and distribute a very limited number of connectome matrices, just of the most common ones that people use, but then provide the data and the tools that if people had a preference for some other configuration, they could reconstruct that after the fact. So there's a GitHub repository available that shows both the code that was used for generating those connectomes and the intermediate data. Some of the changes that I've made to Matrix 3 to expedite that. And I also made a point of all of the internal project discussions that we had regarding these decisions. I made sure that those happened within GitHub so that at the point when the manuscript was submitted, we could actually make all those discussions, move them into the public domain so people can see how we came about those. So maybe there's some interesting insights in there. So one of the first decisions we made was about the anatomical segmentation for doing anatomically constrained tractography. I have a particular algorithm that I often encourage people to use for adult brain data that operates mostly on the free surfaces, but it is quite expensive to produce. So here we decided that, well, if we do something that takes runs 100 times faster and gets you most of the way there in terms of the benefits, well, maybe we'll use the simpler approach for this particular project. And I also implemented a couple of things whereby if UK Biobank had already pre-calculated certain data that we could make use of, well, I'm going to augment my script to make use of those data because that's not a lot of additional computational expense, but maybe large benefits. The second was around this idea that sometimes when we generate connectomes, what we do is we sample values from some quantitative image along the length of each streamline, and then it's those values that go into the connectome. And so you're taking your tractogram, you're taking some 3D quantitative image, and you're sampling values along its streamline trajectory. And so here we're generating 10 million streamlines per session. So we have 10 million values where each is the mean of that particular quantitative image. But we had a large number of quantitative parameters that we wanted to be sampling from. And the issue here is that these tractograms are quite large in file size. And so doing this process 7 times independently, that's 7 reads independently through a very large file. So that has a lot of, excuse me, hard drive IO overhead. So what I did is made a modification of the relevant Ematrix command that's called track sample. In that first, I would generate a 4-dimensional image that contained all 7 of those volumes. And then you would only have to run this command once, and it would internally loop over those 7 volumes, sampling each of them, and produce a single output file. And so that just reduced the amount of redundant calculation happening. When it comes to retrospective reconstruction of connectomes, we made the observation that, well, typically when you're generating a connectome from a tractogram, you don't actually need the full trajectory of each streamline. You just need the endpoints in order to assign them to the relevant grey matter parcels. So we didn't have to ask UK Biobank to distribute 45,000 tractograms of 10 million streamlines. We could just reduce them to the endpoints and cut that size quite substantially. Another thing we did related to these quantitative parameters is you need to encode these scalar quantities somehow. And given the imprecision of tractography generally, we decided that, well, we don't need these things to be super precise, so we can actually use a reduced number of bits per value and still retain performance, but halve our storage space. Unfortunately for me, while these kinds of tools are very easy to use in Python, it took several thousand lines of code of C++ to embed the support properly within Ematrix 3, but it now means that once this is part of the next major release, it would be possible to use the MPY format across a multitude of Ematrix commands. So at the far end of the spectrum is this project that very recently got accepted. It's still in journal preproof as of yesterday. So this group came to me because they had a particular analysis that they wanted to do that was literally computationally intractable. Their local high performance cluster refused that they were going to allocate them that amount of resource. And the reason was they had this massive looping structure where they were capturing white matter abnormalities based on TL-weighted imaging. They were using tractography from a large number of human connectome project datasets, and they were doing non-parametric shuffling of their data. So when you write that whole thing out in this pseudocode, what you find is that this was going to require tens of millions of CPU hours. And the main problem was that they had this process of taking a whole brain tractogram and taking a mask and looking for intersections between the two. The trouble is that this expensive process was embedded very deeply in this great big algorithmic loop. So without going too far into the details, essentially I implemented for them a tailored C++ implementation for their particular project. And by exploiting various algorithmic designs, I was able to speed this up by around 1000x, which then meant that it was computationally tractable. So as quick closing remarks, I would encourage people to not be too precious about their tractograms. Sometimes people start talking about computational problems and storage problems because they've got these massive tractograms and they're trying to save all of them. I would encourage, like with the UK Biobank project, putting a bit of thought into what you need to compute and what you need to store. As a very high level question, I would comment that streamlines is technically not the only form of tractography, and I do wonder sometimes if we're shooting ourselves in the foot. And something I've been thinking about a lot more recently is the extent to which people need to be putting thought earlier on, even at the granting stage, into explicit funding for research software. So do you need to engage someone like myself who has experience with a particular API that can implement things, or do you need to be employing someone with that specific set of skills? That's all for me. Hopefully that seeds some interesting discussion.
Great. Thank you so much to all the panelists. That was really great, a great spread of different topics, and I think there's many intersections and kind of things that we can discuss across all of those. So for those of you who are here on Zoom, you're welcome to use the feature that will let you raise your hand if you'd like to unmute yourself and ask a question from the panelists, or feel free to type your question into the meeting group chat. And I see there's already a question. Please feel free to mute yourself. No.
Hi, everyone. Thank you very much for this insightful lecture. I have a quick question because I'm neurosurgeon and currently doing my PhD thesis regarding intracranial hemorrhage with the minimal invasive surgery, and we aim to use tractography, as at the early phase. But I did recently the literature review, and it might be I found that deterministic method is quite difficult because hematoma, because of the hematoma, and most authors use probabilistic. But now I saw again all this stuff regarding the bundle segmentation, and also the technique that you described previously. I forget. I will try to catch up more with the presentation. But I want to know, what do you think about the use of tractography at the early phase, and to integrate metric derivative from this tractography in the clinical implication for patient?
Great. Yeah. So maybe if the panelists want to sort of comment on how this enables clinical applications, these advances. Francois, do you want to take that one? Sorry.
But if I can answer, like you mentioned in the chat, like which metric you can derive from tractography and map it to bundle. First, as always, it really depends on like what's the direction you want, like what's your like clinical question. Like a lot of people use the FA to mean a classic white matter integrity, like that's something a lot of people in the field don't like, because FA does not mean good white matter. But also, like if you're interested in surgery, sometimes I personally like to use a streamline themselves. Like looking at a metric does not really help, but looking at the shape, the volume, the curl, the span, the surface area, the torsion, all of these things can also be very useful in surgery. It's very hard to conclude something from, let's say, FA in a bundle in surgery. Especially because you have edema, or you have the quality of the acquisition can sometimes be a variable. So it really depends on what you want to show. If you want to show a symmetry, for example, is the bundle on the left the same as on the right when there is two more, for example, using the streamline themselves as an object for the shape and the symmetry is sometimes, to me, more interesting than trying to map
Okay.
an FA value to it, especially in the case of surgery.
Okay, so if I understand you well, you recommend that it is better to go to qualitative, if I can say it like that, qualitative metric. It is better than to use this quantitative metric regarding FA, which is might not be reproducible, because what I saw also is that this value of FA is high variable regarding the type of track that we are trying to map, because I saw this high intervariability into the clinical study that I did just recently in the review, and that's why I really I try to come here to follow this webinar. It is the second time that I assist to your webinar on tractography. I am currently in France, and I think that you have another things in Bordeaux in October. If I will try to attend, because maybe it should be interesting to discuss a little bit more regarding my project with you. I want to, because currently what you mean out makes so much sense. But we need to classify it correctly to be able to use it in clinical setting, because we cannot just say we will just do this or do this. So we are trying to have some protocol to include the tractography in our criteria decision. So I think I will reach out to you. Yeah.
Yeah, I
Yeah.
don't want to take more time
Thank
for
you.
Robert as raises hand. So it's really custom. So like depending on what you want to do, there is no like a clear-cut solution to solve everything. So Robert, if you want to pitch in.
Yeah, I'll throw three responses to that. One is that the problem with acute ICH tends to be the parameters that you get from your Voxer-wise model. A lot of them become quite unreliable. Certainly my metric of choice being apparent fiber density from pseudo-Goodey convolution can do very strange things with acute brain injuries. When it comes to these kinds of clinical things, I would definitely push people towards probabilistic rather than deterministic tractography, because you don't want deterministic tractography giving you an erroneous sense of specificity and potentially having false positives. Relating back to some of the stuff I presented, if you're finding tractography unreliable in these kinds of acute injury cases, you might want to consider something like what we did with the multi-scale heterogeneity work, whereby you just use volumetric segmentation of your individual subject, but you use tractography data from HCP subjects, and you try to combine those together in template space to get a sense of estimated affected bundles given the location of the infarct.
Great,
Okay,
thanks.
thank you very much.
Are there other questions? I can ask one, I think. So I think, oh, Kurt, please.
Yes. Sorry, I was actually just finished typing it. So I'm going to hit enter and put it in the chat window, and then I'll ask some of them here. I actually wrote 4. I don't know if it's appropriate to go through all of them, but I'll start on the 4th one. And this is just because all 4 of you develop, maintain different softwares and packages. I thought this would be a fun question to ask you, especially related to a lot of these issues that we're facing and that you're overcoming. What's the most common issue problem you see on your forums or pages? And what do you think can be done to solve some of the common issues you see in tractography or working with these streamlines? And then there's more questions too throughout if you're looking for more questions and topics.
I can go first. I didn't see anyone raise their hand. So the most common, do you mean the most common problem with the code or with the usage of the code? Like just to like, do you term bug or do you think like usability? Just to clarify your question.
Both. I think they're all important for people here developing, using, interpreting these things.
Yeah. So the most common thing is when people switch from MR-Tricks to DipY to DSI Studio, my most, I'm sure Kurt and Ariel know that, it's the spatial relationship with the streamlines. Are they aligned with the right thing? Are you in the right space, the right voxel size that you think you are? Are they overlapping in the right software? Like, are they overlapping in MR-Tricks versus DSI Studio or DipY Horizon? Also invalid streamline, like some software, they support streamline of 0 point. It's like a ghost streamline. And some software support streamline with 2 points, while other software don't. And all of those tiny difference between software, between file formats, error in computing, like you do a thing in MR-Tricks and then you switch to DSI Studio and it's not really a bug, but it's a known issue that they don't talk about, I don't know, streamline with 1 point. These small problems are a huge limitation to interoperability, but also the desire of people to prototype a solution, like to go from their idea to the result can be, I start with MR-Tricks, I go with DSI, and I finish with Scilpy. But if there is a tiny problem in the middle of all of these transitions, then their solution doesn't work. So they need to stay within one software, or they need to contact people for help. They send me an email saying that my software doesn't work, and I say it's not my fault, it's Rob's fault. And then like, not really, I'm joking. But the idea is like, it's this friction when you transition from software to software, from script to script, tool to tool. This is the #1 difficulty I encounter. I see Rob raises them.
Yeah, do you want to add, Rob?
Yeah, as far as the most common question, that's a hard one. We get a pretty broad spectrum. We don't get too much repetition, which hopefully means people are using the search function, and a lot of stuff's been answered already. If there's one thing that does crop up consistently, it's probably how many streamlines should I generate? As a bit of inside baseball there. As far as the question regarding the UKB data, the full tractograms no longer exist. There was just no way to preserve all of it. So the closest you would get for bundle specific measures would be if you were to define a bundle as subsets of parcellation endpoints, and then you read your mean quantitative values from the corresponding streamlines. That's as close as you're going to get. If you wanted something that was specifically about tractometry rather than connectomics with UKB data, you'd probably need to do a whole lot of reprocessing. I did push for them to distribute the estimated ODFs. I don't think that made it through, so there's a bit of recomputation there.
Yeah, just to add maybe to Francois's comment from before, I think, yeah, the coordinate frame issue is and kind of transformations between different coordinate frames. As an anecdote, I was on a meeting with an astronomer earlier today, works on a very big project, and he was describing sort of the final work on the pipeline that processes the images. And when asked sort of what was the crux of the problem, this person also said coordinate frames, like there's the sky, there's the camera, there's the telescope. All of these things have coordinate frames. So this is common across fields as well. John, do you want to add?
Yes. Yeah, I think what's already been mentioned about coordinate frames and then working with different softwares is common. It's also common, even though we try to make it as easy as possible to install, there's always issues with people trying to install it, and there's some error. We're eager to help with that. But I think in general, a lot of our issues fall under the category of we're all like researchers. So we're all using the software for our own projects. And we try to make our software as flexible as possible, but everyone's using it for like a different use case and wants to do their own not everyone, but most people want to do their own sort of custom thing with it, and maybe not just run the generic pipeline. And those I think are pretty interesting because we all write open source software. So with those issues, it's sometimes the case where it's something that we've thought about as our lab, or it's easy to implement, and then we'll go off and implement some change to the code to accommodate what another lab wants to use our software for. But it's also really nice when people maybe like read the code and could potentially like see if they can make changes to the code. But that is probably the most common issue. And I think sort of promoting open software is a great way to help with that.
Robert, do you want to add?
Yeah, I'll just latch on to another one of Kurt's questions asking about something you would think would be fairly trivial, which is when does a streamline touch a region of interest? But there's actually a lot of different ways that even that process can be done. You might think, well, you just look at each streamline vertex and which voxel is it in, and is that voxel part of the ROI? But quite often we do more fancy stuff. We might upsample the streamline first so that it doesn't jump over any voxels. And then there's how do you interpolate the trajectory of the streamline between the sampled points? Is it linear? Is it higher order? Or even in the tractography processing space, there's a lot of people using this concept of blurred streamlines, where you either consider a streamline to have some kind of radius associated with it or like a point spread function. So these all make a seemingly trivial operation quite complex. And I always encourage people to think about what is the raw data and what is the actual algorithm being run, because sometimes if these nuances become important for your experiment, you need to be across them and understand how inadequacies in those processes might manifest.
To add on to that, we recently changed our software for if you're detecting how close a streamline is to a region of interest. We actually transform the regions of interest from binary maps to distance maps, and then you can use then you can interpolate along streamlines in these distance maps. So the 3D image is a 3D image where each spot in the 3D image is how far away you are from a given ROI, and then you can interpolate along a streamline and then ask with some threshold, how close did you get to an ROI? And that's been that's fast for us and flexible as well.
If I can add something else, also don't be scared to ask more questions. Don't be intimidated by Kurt's wall of questions. Feel free to add more. But to just finish up on this, a challenge related to this question. In Python, it's fairly easy to hack a solution fairly fast. So basically, if you ask me, like, is a streamline kissing against a region of interest, like, is the streamline going parallel to the thalamus at some point? Like, at some point, they run parallel. They don't touch, but they run parallel. I can fairly easily come up with something in Python in one day. And then I'm going to send it to you. You're going to test it and say, oh, that's not what I wanted. It's not exactly what I wanted. And then I'm going to change it. And like one of the challenges, not in Python, at least, not the algorithm itself, but it's to frame the question. What Rob was saying is like, it's not as easy as does it touch or does it finish in? It depends on the data, it depends on the resolution, it depends on the use case. And then someone revealed, I'm not working with human, I'm working with mice. And then, oh, all of your threshold and your distance are not right. So one of the difficulty for me is not the algorithm, is to pinpoint exactly what the person wanted. And this is very iterative, and that's always a challenge. Someone has a challenge, I think I solved it, and then they reveal something I didn't know, like, oh, I'm working with blur streamline, or I have super high res resolution. It's not a 1 by 1 by 1, it's nanometric. So this changed everything. So that's one of the challenge, is not necessarily the logic of it, it's the actual data, dealing with the real life situation. Which is not the same in C++, for example. C++, I don't think Rob will ask something really fast without answering all of those questions first, because the development in C++ is probably a bit harder, but you need to be sure of what you're doing. In Python, I don't do it like that. I do something quick and then I figure out I did the wrong thing. So it depends.
Yeah. So for me, it's possibly less of a programming language thing and more of a software design philosophy thing. So with MRTrix 3, we very much go for the Unix philosophy of having a large number of tools, each of which has a very robustly defined purpose and scope. So often when people are requesting a certain feature, I'm not looking to implement precisely the thing that they requested. I'm looking to implement a general purpose tool, one use case of which solves their problem. So I'm trying to push the solution further towards the all end of the spectrum. But it can take a fair bit of experience to actually identify what is the general solution to this problem rather than what the person's actually asking for.
And sometimes like 2 or 3 scripts together will end up being the solution, but the user will have to combine them because you don't want one script to rule them all. So is there other question?
I see no other questions. I think we're also at time here. So thank you again to everyone who attended. Thank you so much to our speakers. And stay tuned for messages about Tract-Anat in May.
Thank
Thanks
you very
a lot.
much. Thank you. Bye.
Thank you.
Yes,
Bye.
bye all.